Fernando, and thank you for this kind introduction. And everybody, good afternoon to everybody, and thank you for joining this ISGAN webinar that is about the planning of distribution systems in the new era of smart grids. And just this is okay. Just let me show the deadline. Okay, this is a brief outline of the presentation. Just we will have few slides about the ISGAN. And what is ISGAN? ISGAN is a strategic platform to support high-level government attention and action for the accelerated development and deployment of smarter, cleaner electricity grids around the world. And as you can see, it's an initiative of the Clean Energy Ministerial, and it's also organized as the implementing agreement for a cooperative program of smart grids. And ISGAN is divided into 8 annexes. And as you can see, we have one about the global smart grid inventory, then we have smart grid case studies and cost-benefit analysis toolkits. Actually, currently, I'm the leader of this annex, and then we have Annex 4 and 5 for decision makers and Smart Grid International Research Facility Network, and then we have Annex 6 about power transmission and distribution systems, and Annex 7 is about the transitions, and then we have the ISGAN Smart Grid Academy, that is the organization that promoted this webinar and many other webinars. And this is the geography of ISGAN. As you can see, it's really a huge organization, and almost, well, we have countries from all over in the world. And I don't have time to go exactly to list all the countries, but you can see the flags in the slide. And so now we can start with the presentation, and the first group of slides is about the context and the motivation of the activity. And well, everybody knows that we have some key drivers that are motivating the change, and we have for sure environmental and regulatory pressure. We have a market liberalization and the need for improving efficiency in energy supply, and for sure we have to improve the security of supply and the reliability and increase the quality of services. And well, we don't have enough money for any kind of investments, and so it's very important in many companies to postpone investments on copper, on hard infrastructures. And we have a lot of dispersed renewable generation in many countries, and this part is also now followed by many other countries. So just to give you an information, in Italy we have almost 20 gigawatts of dispersed generation installed and connected to our distribution systems, and 1/3 of energy is now in Italy produced with renewable generation. And finally, in order to manage this huge amount of new generation, we need much more flexibility in the system. So also flexibility is a key driver, and under this topic we can count storage, electric vehicles, and active demand, and etc. So now decision making is a really hard job, and you can see that we can split operation and planning, and then we were used to have a long-time decision in planning, a real-time or near real-time decision in operation. But now the trend is to make the cycles shorten, and this is particularly in planning is very important. And another point is how to generate different alternatives and different scenarios. Particularly this is very important in planning. But now we are facing a much more uncertain situation, and so the future is really foggy, maybe more foggy than in the past, and it's very difficult to realize the impact. And so we should manage better the risk that are behind our decision. And if I go to to planning. In demand forecast, where we were used to be based on macroeconomic and historical models, but now we have to forecast also not only load, but also the distributed generation production and renewables. And for load data forecast, the most important fact is that in many countries we have smart metering, and so we are going to have a lot of information, and we should use this information in our planning studies. And another important point is the way we generate alternatives, and well, the most important point is this. On this is that we should consider active network solutions, and that means we should consider the operation also inside planning, and this is something new. And also another point is about the approach. We were used to be based on deterministic models, and now we believe that it's better to switch to probabilistic models that are more suited to the application in the new world. And this is one of the, you can find a plenty of definition about smart grids and about active distribution networks. I have used a CIGRE definition that is, but you can find similar definitions from other international bodies. And you can see active distribution networks have systems in place to control a combination of distributed energy resources defined as generator, loads, and storage with power electronics. All these resources have a lot of power electronics installed. Distribution system operators have the possibility of managing the electricity flows using a flexible network topology. This is another important point. And DER takes some degree of responsibility for system support, which will depend on a suitable regulatory environment and connection agreement. So we are talking about how to consider smart grid in future planning. Short term, I think that this presentation is more focused on medium to short term planning, but some of the concepts can be extended also to long term, but maybe we can discuss later about that. And what about distribution planning? We have different options for systems development. We have for sure primary distribution voltage, then we are talking about voltages that are inside a range between 1 kV to 66 kV generally. This is from country to country there are some differences, but this is quite a common range of voltages. And we have different way to have the system, and we have different network architectures, but the most common is the radial or the mesh, and then we have possible different paths in the system. Then just few examples of the star, and then we can have very long feeders, and then we can find a good compromise between possible different options. And the distribution planning is motivated by different factors, and these different factors can define some objective function that we can use in planning. And for sure, we should look at cost, and then we have capital expenditures, and we have also operational expenditures, so we have to look at building, maintenance, losses costs, and we have to consider in planning the load, particularly load density. Maybe urban, semi-urban, rural areas are typical examples also of different load densities. And then we have to include in planning also environmental concepts like the presence of lakes, forests, historical buildings, but also they need to be green and to facilitate the connection of renewables and so on. And another important point in planning is a must now, is we have to consider the continuity of supply, and many countries have regulation based on penalties and rewards for DSOs. And one important point is that we should include in our planning studies the role of network automation. And anyway, optimal distribution planning is a very NP-hard problem, and it's a very complex problem. And distribution planning is normally about the evaluation of different options, alternatives. And maybe just to give you an example, we can consider the feeder calculation. And for feeder calculation, then we have to talk about the demand. The low demand is not really a certain data, but medium voltage level uncertainty is reduced because of the aggregation of several customers. And normally we use to represent loads in load flow calculation with a single yearly power demand, maybe as an example the peak value, or with a unique load profile. And then we can repeat the calculation for each hour in a year. And we do some simplifications in the calculations, and maybe of these simplifications can be assumed because of the typical radial configuration, but with distributed generation, these assumptions are no longer usable, or they are not so simply usable because with the distributed generation we don't have unidirectional power flows. And in the past, but actually not only in the past, we are using a deterministic approach for network calculations, and so we assume to know the data without any uncertainty. And those data are the annual power demand, the annual power generation, and the power demand growth rate, and so on. And this is a typical planning process, and we have proposed in CIGRE to many DSOs. And the typical planning process at high level can be reduced to 6 steps. One is the gathering of information from markets and customers, and then we can forecast the demand and generation. Then we do some network analysis, and then we can find and propose different alternatives, and then we have to evaluate and select some of these alternatives, and finally we have to design the selected alternatives. And this is the answer we received from DSOs worldwide. And as you can see in the chart, there is a very good alignment between our definition of planning process, high level definition of planning process, and the answers we received. More than 90% of respondents confirmed that to perform the steps of this typical planning process. And if you look at to this slide, you can see that just few companies really use the potential of smart grid and new technologies in planning studies. Every company in the world is talking and is studying and is claiming to consider smart grid options in the development of the system, but if you go inside, they don't really use smart grid options in day-by-day planning activities. And this is the results of the survey. Most utilities make little consideration for active network solutions in planning. And there are some good reasons for that. One reason is that we don't have reliable planning tools and methodologies in order to really include smart grid opportunities in planning studies. And the other point is that there is also a lack of good business cases on that. So what we have done is investigated a little bit on that. But before going on the future steps, maybe we can have a look at this high-level flowchart that describes the traditional distribution planning. Just to give you an example, you can produce different flowcharts, but this is just to give you an idea of it has been done in companies so far, and then I can propose some change, and then we can discuss later on about this proposal. And then you can see we have the definition of the planning study. Maybe we are talking about the expansion of a distribution network, or we are talking on how to face the load growth in an area. And then we have to find some planning alternatives, and then we do normally deterministic network calculation, and we see if everything is okay in the system, and if not, we can do something. Maybe we can build a new line, or we can revamp existing infrastructures in order to make the system good and to comply with all the technical constraints we have. And finally, when everything is good from a technical point of view, we can evaluate. So we have the cost evaluation of this planning alternative, and finally we can go to another alternative, to another option, and finally we can find to rank the different alternatives in order to complete the decision making and decide what is better to do. And what is important in this slide is not really the flow chart, but it's that we normally use deterministic calculations, and so the question is, would it be better to use probabilistic models, and for what? And we use simple load models, and maybe we can use more detailed load models, particularly because we are going to have a lot of information from smart meters. And another point is normally we don't have really operation at the distribution level, because operational issues were fixed at the planning design stage. The system were designed to be so robust and so robust that any issue were fixed and solved in advance. And another point is normally we use a single objective functions, or we use a combination of different multi-objective functions with weights in order to have just a single function. And so maybe this is something that we can improve in order to make the planning process more suited to the smart grid. And about the deterministic calculation, we should consider that the occurrence of worst scenarios is very rare, and so we invest a lot of money in some cases for nothing. And just to give you an example, in order to increase the reliability, normally we have a radial system in the distribution with some emergency connection, and in order to use those emergency connections, we have to lock some feeder capacity so that we can use some portions of the network to supply from using other parts of the load. But we don't really use that capacity, and maybe we can do something better with a smart grid. And another point is that the identification of worst case is not so objective, and we don't have any way to assess the level of risk that is related to the choices. And so these are some of the reasons to make some change. And so now I'm going to the novel distribution planning with some examples. So the need for new planning. Electricity is now produced by renewable energy sources, and most of these sources are connected to distribution systems. And the production is closer to consumers, and we are also going to have a lot of new way to use energy. Just an example is the electric vehicles. And we are going to have markets, and new markets also at the distribution level, particularly the distribution system can offer system services to the power system as a whole, so it's something that should be included in planning. We have a lot of information and communication technologies, and so we have a lot of information that a lot of data that we can use in our planning studies, and we have also automation, so we can reconfigure the network, or we can control and coordinate the generation and also the way we use the energy. And we can also consider that storage is another opportunity that we should consider in planning. And this is a table that we have prepared, and this table is not from academia. This table has been prepared by a DSO in Ireland, and as you can see, what is interesting, that we have some technical issues point out, typical technical issues like voltage rise drop, like the hosting capacity, the reactive power, support or protection. And you can see that we can use some business as usual actions, and also we can do a lot of things with the smart grids or active distribution networks, as you prefer. And just to give you just one example, voltage rise, we can add capacitor banks, voltage rise and capacitor banks. Maybe if we have voltage issues, we can use capacitor and SVC, but we can do also a lot of things by coordinating the dispatch of the DER, and so we can do a lot in the system by simply including our planning studies also the opportunities that are coming from a more active system. And so we have the idea here is to reduce less traditional network investments and to increase more cost-effective active distribution actions. And so this is in a nutshell what we are proposing in CIGRE, and I'm very glad to see that as chairman of CIGRE 6.5, that is the session of CIGRE that is devoted to distribution system development. I'm glad to see that year by year the number of companies that is accepting this proposal is increasing. There are many DSOs worldwide that are starting to include these suggestions in their planning methodologies. And so the proposal is to enhance load and generation representation by using time series, by using load and generation profiles, and to increase the description of smart grids in models that are used in planning. And we should include in our models the role of information and communication technology, the role of distribution state estimators and measurement systems, and so on. And another point is that we should leave the deterministic approach in order to consider the probabilistic, risk-oriented planning, and increasing the multi-objective. We should manage the risk. And the other point is that we should add in our planning also the operation actions. And this is just the list is just about some of possible actions: volt-var regulation, power congestion management, generation curtailment, demand response and flexibility, storage and electric vehicles, let's say VTG, something like that. That means that, just to give you a clear example, if you have to build a new line, maybe you don't need to build a new line because you can ask someone to do something when there is an issue. And this is the main difference between the traditional planning and the new planning paradigm we are proposing. And this is the high-level flow chart we are proposing. It's very simple, but just to give you an idea what we are proposing. As you can see, the flow chart is a little bit more complex than the traditional one. And we have some new boxes. And one is about the customers' data modeling. And then, then we have another block that is about the probabilistic calculation, that is something more complex and different. And after the probabilistic block, we have to assess the risk, and we have to decide if the risk is acceptable or not. If it is not acceptable, it doesn't mean that we have to build a new line or we have to build a new system, but maybe we can make the risk acceptable by simply managing in a different way the system. And so this is the block to the left in the flow chart. And then we have some kind of active management, the non-network actions or solutions, in order to make the risk acceptable. And the other point is that the assessment of each alternative design option is not a single objective based, but it's based on a multi-objective alternative. And I think that we can go. This is the point. We are talking about the customer's data modeling. It's not a snapshot of the operating conditions. We should use better and more smart meter in order to gather information from the field and to build reliable models of loads and generation. And in this sense, the application of big data and clustering techniques are very important. And I think that there is a lot of room on that topic for research, a lot of room for research on that topic. Just to give you some example, this is from Manchester, and you can see the classification of all states in a year grouped into some typical conditions. Then we can have some clusters, and then we can work on clusters instead of profiles. But the clusters are built starting from real profiles, and this kind of application has been used in the academia. I mentioned Manchester University, but it is now also used and proposed in a company. EDF is proposing a very similar approach in order to increase the level of information and to make the use of this data simpler. And another way is using some typical days that are also obtained by analyzing real data, and we can have also an uncertainty band on profiles. And you can see this is another way to increase the level of information to be used in planning. And this is another way to increase, to use smart meters. It's a very recent activity in Norway. It's a PhD thesis from Dr. Tonne that is working with a real DSO in Norway. And in this case, you can see on the left that's the traditional models to represent the load, and there is a comparison between the traditional way to represent a load. This is a grocery, and with the real data. As you can see, we are using models that are really not really a good representation of the reality. So we have to use the data from the smart meters, and if you use the data from smart meters and you leave deterministic models and to probabilistic, you can see on the slide, this one, you can see that you can reduce investments and you can postpone a lot of investment in your system. Another important point is the probabilistic calculation, and again, this is something very important. This just to talk a little bit about different ways to approach probabilistic models. We can have probabilistic load flow, we can use Monte Carlo, we can use fuzzy set theory, as you can see. But what is really important is that we can manage in an objective way the risk. For sure, the level of risk that we can accept is something that is not that easy to establish, but we can manage the risk, and we can define in advance the risk that we can accept. And this is an example in a real case, Italy. This is a distribution network in the Lake of Garda. We have 140 medium voltage to low voltage secondary substations, and the demand is about 8 megawatts in this small area. The network is weakly meshed, even if it is radially operated, and the planning period is 5 years long, and the demand growth is 2% per year. And the question is, do we need a new primary substation? That means station 150 kV to 15 kV, and to 20 kV. And the other point is, do we need this new primary substation because we are building a new touristic area that is going to ask for 4 megawatts. And just to give you an example, we have studied this system with a traditional approach and with a modern planning approach. It is based on a probabilistic network calculation. The level of risk, accepted level of risk, is 55%. That means there are 95% of probability not to go beyond the limits in the voltage and in the thermal capacity of lines and something like that. As you can see, in this case, there is not really a good reason to abandon a traditional planning approach. And the reason is that we know very well the load, and so we don't need to leave the traditional planning. But if we add some uncertainties, and the uncertainties are represented by the presence of fast charging stations for electric vehicles, because this area is very beautiful. We want to reduce the level of pollution, and so we want to reduce the number of fuel cars, and we have to increase the number of electric vehicles. Well, in this case, you can see there is a very important difference between the traditional planning and modern planning. The savings are very significant, and the and we can manage the risk without spending a lot of money for upgrading the network. And so the message here is that the higher are the uncertainties, the higher is the worth of probabilistic approach. Another point I want to show you is about the active management and how to include and what is the worth of smart grid in distribution planning. And sorry, okay, and for sure I want to show this also talking about multi-objective. And multi-objective means how to find a good compromise solutions for conflicting goals of stakeholders, and how to manage different objective functions, not only cost. This is very important because sometimes we cannot monetize everything, and with a real multi-objective planning, we can manage different objective functions. And the problem is that with the multi-objective we don't have an optimal solution. We have a family of good solutions. So how to select the best one? Okay, decision making is an important tool now, and particularly multi-criteria techniques are very good for that. We have used in order to identify the best options for storage, and to help our regulator to find if it is allowable or not to add some storage in the distribution system. So we can say that decision-making based on multi-criteria is a good option. And this is just to give you an example and to show that the very simple flowchart of traditional planning can become more complex if we had multi-objective, probabilistic, and the smart grid operation in the planning study. And that means that there is an increasing of complexity in planning, and we do need methods and techniques in order to manage the complexity of new planning. And a final example, a comparison, you can see we can compare 5 different planning studies on the same small network, just to give you an idea. And then we have the deterministic fit and forget, then a simple probabilistic approach with different level of allowable risk, and then we have the active management of the system, and finally also storage installed in the system. And I want to show this is an example, very simple, it's a very small network, just to give you an idea. And the problem is that we have to connect in this system 5 new PV generators, and we want to see what happens in the network and what kind of investments we need. And the result of the deterministic for sure is the more expensive. We have to build a new trunk line, we have to refurbish existing trunk feeders, and we don't have to do nothing in the lateral branches of the network. And we have to spend for capital expenditures more or less 1,040 and 400,000 kilo euros. But what is interesting is that we simply leave the deterministic approach and we consider the probability of issues and voltage and power congestion. Then we can reduce the level of investment. And for sure, we have to assume which is a lower level of risk. And in this case, we have low risk, 5%, and we have high risk. But as you can see, the level of investments that is necessary in both cases is significantly smaller than the investment the capital expenditures we need with the deterministic. And the quality of voltage is improved, so we are not reducing the quality of services in the network. And if we add active distribution network controls, we can further reduce the capital expenditures. The reduction is not that much because we have just we don't have so much dispatchable DER, and so that's the reason because we don't improve so much. But if we include the demand-side integration, if we include the active demand, maybe we can also reduce further the capital expenditures. And finally, the storage. In this particular case, the storage is very useful, and we can again reduce the expected capital expenditures in the system. And so you can see in the chart that from the traditional planning to the new, we can really reduce capital expenditures. And this is a chart just to show that the voltage is good in the critical nodes, and what is really important is that we can manage the risk, and we can exactly know for how many hours per year we have to ask someone to do something. This is very important also for customers, not only for DSOs. And finally, an example of the software. There are some software that are capable to manage this kind of new application. This is a software we have developed here in Cagliari. Just to give you an example, there are some planning tools that are really capable to do most of the things I have showed you. And just to give you an example, a very simple case, but look at this table. Please, on the left, there is a typical fit and forget planning on the same case, the same network, the same PV to be connected. And then you can see that we have, to the right, there is the classical one, to the left, the new one. Look at the upgrading cost, the cost for the system in the same period with the same level of risk. Actually, we don't have to do almost nothing. And on the other side, we have to build a lot. And from another important point is that joule losses. With the smart grid, we want to exploit our assets at the maximum level, and so you can see that the joule losses can increase, and this is the bad phase of using a smart grid for postponing or avoiding investment in the system. Future works. Well, there is a lot of room for research in this field. We have to include low voltage systems in planning. It's not that easy. The modeling low voltage is very complex. We have to use 4 wires models, and the closer to the load, the more difficult it is to model the load. So this is a very hard job. And we should include the role of active demand in planning. And another point is, well, we want to model everything in our planning studies, but the time granularity of model is very, very important. Otherwise, it's very difficult to find tools that are capable to give good results. And I think the other important point is to include in planning not only electrical energy, but to include in planning multi-energy and multi-service. And this is something very difficult, it's very cumbersome in many cases. So this is, there are 2 pictures before the conclusions. This is a picture that is very, very difficult to read, and I apologize for that, but it's almost impossible to read. But I don't want you read this picture. I want you just you look at the colors. The green means that there is no problem. The red means that the network has problems, and this network is an Italian rural network. It's a representative network. and the projection is a forecast to 2020, and this is a classical passive operation, and that means that every day and every hour on the day we are expecting to have issues. Some issues are, this slide is about voltage. Red means that the voltage is too high or too low, and as you can see, we are going to have a lot of problems. High voltage is due to the presence of photovoltaics, and the lower is due to the increase of load in the hours of the day when we don't have PV. And this is what we are expecting to have with a real smart grid in place. As you can see, that we can fix all issues without any investment by simply operating the networks. And this is exactly what we are doing now in Italy. Now we have a very strong regulation that is promoting smart grids with an output regulation. DSOs can receive money if they increase the level of smartness in their system. And by doing that, we expect to fix the vast majority of issues with few investments in the grid. For sure, we have to invest in and to spend money to improve communication and information facilities and to improve the network automation. But it is less expensive and simpler in many cases, improving the ICT facilities than building new lines and new power infrastructures. And so these are the real conclusions. And then the first point is that DSOs still adopt traditional planning tools that are not really suited for the future. And traditional planning tools do not really include the smart distribution in the models. And the new planning methodologies are required, and there is a list of possible suggestions for new planning methodologies. And so data modeling and smart meters, operation and planning include the role of flexible demand generation and storage in planning, make risk and reliability analysis explicit. And the other point is that we should co-plan communication and facilities with the power system. And CIGRE is working on that, and CIGRE Working Group C6.19 has finalized the activity with a technical report that you can see. It's the technical brochure 591. And also now we have a new working group working in CIGRE. It's a CIGRE Silent Joint Working Group, the C1 C637, that is again about planning, and particularly is about the integrated planning between TSO and DSO. And I think that this is the last slide of my presentation. I have some backup slides regarding the future works and some examples if you want, but I think it's time for questions now, and thank you for your attention.